Hello everybody, my name is Walid. I would like to introduce the subject of the one-way analysis of variance, which is abbreviated by Anova. We know that Anova test is used to compare for the means of two or more groups. So I will talk about the balanced design. Balanced design here simply means that the sample size for the groups or for the treatment is the same. So first of all, there are some assumptions that should be fulfilled before starting using the one-way Anova. We know that we have some population, and this population has its own parameters, same like the average of a variable and the standard deviation. And for the other population, it's the same. We have the same parameters. And for the third population, we have the same parameters, but with different values. Of course, we can't understand the parameters of the population. So in this case, we use what's called the sampling process. For example, we draw a sample number 1 from population number 1, and this sample should be representative, okay? And if we make some calculation for the statistic of the sample, we get the average or the mean of the variable we are interested in. We have the standard deviation, and we have a sample size, which is called N1. Same for sample number 2, we have these statistics, and for sample number 3, we have these statistics. We called this type of Anova to be balanced because the value of N1, which is the sample size drawn from population 1, is the same as N2 for sample number 2, and it is the same as N3 for sample number 3. Regarding the parameters of the population, there should be an equivalence between the standard deviation, which means that the standard deviation for the 3 populations should be the same. Sigma 1 is the same as sigma 2, same like sigma 3. So this is one of the assumptions. The other assumption is the randomness, which means that drawing the samples from its population should be in random process. And the other assumption regarding the samples is the independency. Independency simply means that drawing and calculating for sample number 1 does not affect drawing and calculating for population sample number 2, and the same, it is not affecting any statistic in sample number 3. The last assumption is that one-way Anova, we are examining or dealing with only one independent factor. So these are all the assumptions that should be fulfilled before starting using the one-way Anova. Okay, let's examine this question in order to understand what is the one-way Anova and how we can carry out this test by hand in an assembly line in a factory. So we have assembly line inside the factory. The number of daily assembled products were recorded for 3 workers. So we have 3 workers, which means that we will treat all of these 3 workers as 3 groups recorded on 5 randomly selected occasions. So in this case, we are sure that the randomness assumption is fulfilled. And of course, we will assume that all the assumptions are fulfilled. Below are the number of products assembled by each worker. So below here we have this table. This table is the productivity record for each operator in one day. We have 3 operators, operator number 1 and operator number 2 and operator number 3. And below here we have the data or the observation. For example, these are the observation for operator number 1. For example, in one day, operator number 1 assembled 7 products. In other random day, he assembled more. He assembled 10. In third day, he assembled 8 and 10 and 7. So what is needed here is just to carry out the one-way Anova, but by hand. So we need to make all the calculation for the one-way Anova manually by hand. What's the purpose of the one-way Anova test? Is to test the hypothesis that state that the productivity of the 3 workers is the same. This is the null hypothesis. And regarding the significance level, it is 0.05. So this is our question. We need to understand all of the one-way Anova and how to calculate for each parameter. This is the one-way Anova table. Let's examine what does this table includes. First of all, we have the source of the variation, and we know that for the one-way Anova we have 2 sources of variation. The first one is the variation between groups, and the other one is the variation within groups. Then we have to calculate for the degree of freedom for between groups and within groups. Then we need to calculate for the sum of squares, which is abbreviated as S, for between groups and within groups, and for the total. Then we have the mean squares, MS. We should calculate the MS for between groups and within groups. And finally, we can simply calculate the value of the F statistic here. And regarding the critical F, we can determine the value of the critical value for F by referring back to the related graphs and tables. So first we should write the hypothesis to be tested, as we know that we have 2 hypotheses. The first one is called the null hypothesis, which states that the mean for all the population are the same, and the other hypothesis is called the alternative, which states that some of the means are not the same like other. Maybe all the means are different. or maybe two means are the same, but the third one is not. Same like this hypothesis. We can express the hypothesis in other way. We can state that each node, all the three means are the same, and alternative hypothesis, at least one mean is different from the others. So this is all about the hypothesis. First of all, let's calculate the values of the degree of freedom. First of all, we need to calculate or to find the degree of freedom between groups. The formula for degree of freedom between groups is very simple. Degree of freedom between groups, it's equal to k minus 1. K is simply the number of groups. And as we know that we have three groups, we have three operators. So we subtract 1 from 3, so simply degree of freedom between groups is equal to 2. So this is the value of the degree of freedom between. So simply we subtract 1 from the total number of groups. Now we need to determine the value of the degree of freedom within groups, which is called the degree of freedom for the error. The formula for this is very simple. It's called degree of freedom within, or degree of freedom for the error. It's equal to capital N minus K. Capital N means here the total observation for all the groups. And we know that we have 5 observation or 5 replicates for each operator. So the total, or the capital N, is equal N1 plus N2 plus N3. And each of these is equal to 5, so the total, or the capital N, is equal 15. And we know regarding the K, it is number of groups, and we have 3 groups. So we can substitute degree of freedom within, it's equal to 15 minus 3, which is simply equal 12. So now we need to calculate for the total degree of freedom. It's very simple. The total degrees of freedom is equal to the degree of freedom between groups plus degree of freedom within groups. So this is the formula for df total. It's equal degree of freedom between groups and degree of freedom within groups. dfb is equal to, and dfw is equal to 12. So the total is 14. So now we have finished all the calculation for the degree of freedom Now we calculate for the sum of squares, which is called the SS. The abbreviation of the sum of squares is SS. Before starting calculation, or before starting the calculation for the total SS, we need to make some simple calculation regarding the raw data for the three groups or the three workers. Here in the table above, we have here for x1, it is related to the operator number 1, and x2 for operator number 2, and x3 related to the operator number 3. And here we have the observation for operator number 1. We count for the total observation for each group. It is 5 for all. So this is the reason why it's called balanced design, because I'll talk later, inshallah, regarding the unbalanced design. And we have here the summation of the observation for each of these three groups. For example, for group number 1, which is the operator number 1, the total is 42. So simply we can calculate for the mean. It is simply by dividing the total observation by the number of observation, which is 42 divided by 5, and it is 8.4. Regarding the operator number 2, the mean is 10.2, and regarding the operator number 3, it is 11.4. What do we need to complete the calculations? We need to get the squares or all the observations for the three workers. For example, here we have the squares of the observation for operator number 1. And here we have the total of the squares for operator number 1. And here we have the squares for operator number 2. And the last one is for operator number 3. So before starting or before directly calculating for the SS total, we need to calculate the correction factor, which is abbreviated by CF. We need this value or this correction factor in order to complete the calculation for SS total and SS between. The formula for the correction factor is very simple. The value of the correction factor, it is simply equal to the summation of all the observation, and we square all of these observations and divide it by capital N. And we know that capital N is the total observation for all the operators, which is equal 15. Regarding summation of x sub I, it is simply equal to summation of x1 plus x2 plus x3. We square all of these summation and divide by capital N. For summation of x1, it's 42. It is here. We can get it from the table here. This is for x1, and this is for x2, and this is for x3. So 42 plus 51 plus 57, all are squared divided by capital N, which is equal to 15. So by simple calculation, we can get the value of the correction factor, and it is equal to 1500. So the value of the correction factor, now it's ready to proceed further the other calculation. So now simply we can calculate for the total sum of squares, which is abbreviated SS total. The formula for SS total is this formula. SS total is equal to the summation of the squares of the observation for each groups. This is for group number 1 or operator number 1, and this is for operator number 2, and this is simply for operator number 3. All this summation, we subtract the correction factor from these summations. In the table here, we already calculate the summation of the squares of the observation. This is for operator number 1, and this is for operator number 2, and this is for operator number 3. So if we proceed and substitute, the SS total is equal. This is for the first operator, and this is for the second, and this is for the third. All of these we subtract 1500. So simply we can get the value of SS total. So the value of SS total is equal to 46. Sum of square total. Now we need to calculate for the sum of squares between groups. So calculation of the SS between groups, simply we use this formula. SSB, sum of squares between groups, it's equal to the summation of the total observation for operator number 1. We square it and divide by the size or the number of observation for operator number 1, same like for operator number 2, same like for operator number 3, and for all of these summation we subtract the correction factor, which is already calculated. So the summation of the observation for operator number 1, which is denoted by x1, it's 42. Here we have the total of the observation for operator number 1, and here we have the total observation for operator number 2, and here we have the total of the observation for operator number 3. We substitute, okay, and divided by the sample size for each, and we know that we have 5 replicates for each group, and we subtract 1500 from all of these summation. So by simple calculation we get these values, and finally we get the value of the SSP, which is the sum of squares between groups. It is 22.8. So right now we calculate for the SS between groups and the total. What is still the sum of square within groups. Simply we say that the value of the SS between groups plus the value of the SS within groups is equal to the total SS. So this is the formula, and for this formula we have one unknown, which is the SS within. So if we take SSW to the other side, so the sign for this value becomes negative. So SSW is equal to the total SS minus SSB. SS total, it is simply 46, and SSB is equal to 22.8. So the final result here, we have the value of SSW to be 23.2. So by this, we finished all the calculation related to the sum of squares. Now we calculate for the mean squares, which is abbreviated MS. So we need first to calculate the mean square between groups. MS between. Simply the formula for the mean square between, we divide the value of SS between, which is 22.8. We divide it by degree of freedom between, which is 2. So if we proceed, we can simply get the value of MSB to be 11.4. So this is the value of MSB, it is 11.4. By the same way, we can calculate for the mean square within groups, or mean square for the error. So in order to calculate for the mean square within groups, or mean square for the error, we divide the value of SSW by degree of freedom W. And regarding the SS, as we see here in the Anova table, we have 23.2, and the value of the degree of freedom is 12. So direct substitution, we get the value of MSW to be 1.93. So this is the value of MSW, mean square within, or mean square for the error. By this, we have finished all the calculation regarding the mean square. What is still here to complete in the Anova table is to calculate for the value of the F statistic, or calculated F. Now we need to calculate for the test statistic F. Simply, we divide the value of the mean square between groups by the mean square within groups, or mean square of the error. So this is the formula for calculating the value of F, or F calculated, or F statistic. So MSB is 11.4, and regarding MSW, it is 1.93. So direct calculation, we get the value of F, or the statistic F, to be 5.907. So this is called the value of the test statistic, or the calculated value of F. In order to complete all the contents of the one-way ANOVA table, we need to determine the value of F critical. So, in order to determine the value of the critical value of F, we refer back to the tables of the F distribution, but first we should know three values in order to complete the determination of the value F. We need to know the amount of significance or significant level. It's already mentioned in the question to be 0.05. And we need to know the amount or the value of the degree of freedom between groups, which is equal to, and it is called df enumerator in the table. And the third, we should know the value of the degree of freedom within groups, or degree of freedom for the error, which is equal 12. And in the table of the F distribution, it's called df denominator. So this is the expression to determine the value of F. We need to know the significant level and degree of freedom between groups and degree of freedom for the error. If we return back to the F distribution table at alpha equals 0.05, first we should examine this row. This row represents the degree of freedom between groups, which is the same as the degree of freedom for the enumerator, and in our question it is 2. And for this column, we determine the value of the degree of freedom within groups, or the degree of freedom for the error, and it's already calculated to be 12. So the intersection between these two values is the value of the critical F. So the value of the critical F, it's equal to 3.8853. So this is the value of F. It is equal to 3.8853. By this, we finished all the calculation needed to fill the cells inside the ANOVA or one-way ANOVA table. So in order to make a decision or to draw a decision, and what is needed for this decision, should we accept the null hypothesis, which states that the mean of the three operators are the same, or we should reject and accept the alternative hypothesis, which states that at least one of these three means is different from the others. Let's understand what do we have here. Here we have the F distribution graph for the degree of freedom 2 and 12. Here we have the value of the critical value of F. which is obtained from the table. It is a 3.885. This value, critical F, divide the graphs into two regions. The right one is the rejection region, and to the left we have the non-rejection region. Rejection and non-rejection what? We are talking about the null hypothesis. And as we see, to the right of this value of FC, we have the area which is colored by yellow. This is the value of the significant level, which is equal to the 0.05. So how to make conclusion? Simply, we check for the location of the F statistic. This is the value of the F statistic, or the calculated value of F, which we get it from the table. If we return back, this is the value of the F statistic, and this is the value of F critical. So the value of F statistic, it's 5.907. It is bigger than the value of the critical F. So this value, this calculated value of F, lies in the rejection region. So simply the decision is to reject the null hypothesis. And the null hypothesis states that the three means are the same. So the conclusion is to reject the null hypothesis and accept the alternative hypothesis. So this is the conclusion. We get the value of statistic F to be 5.907. It is greater than the value of critical F, which is 3.885. So we reject each node, and each node states that the means for the total groups or the total populations at 5% significance level. So because we reject each node, we accept the alternative hypothesis, H sub A, which states that there is a significant difference between the three workers' means, and one at least of these means is different from other means. So this is what we have today. Okay, thank you. If you have any comment, please write it down. Thank you.